if I can get it to advance. There we go. The canonical giant impact for forming the moon forms the protolunar disk primarily from the impacting planet Theia rather than from the proto-Earth. And because of this, it does not offer a natural explanation for the essentially identical isotopic composition of the Earth and Moon in non-volatile elements, in particular in oxygen, as shown in the plot here. One possible solution to this so-called isotopic crisis is to consider a very different type of impact, a much higher energy, higher angular momentum event. Featured here is a type of impact known as the half-Earth impact, and this is because for this impact, both Theia and the proto-Earth have similar masses that are each about half of an Earth mass. In this type of collision, because of the near symmetry of the collision, the protolunar disk and the planet after the impact have essentially identical mixtures of material that came from Theia and the proto-Earth, so they have essentially identical silicate compositions consistent with the isotopic similarity of the Earth and Moon. But this type of impact leaves the planet disk system with a factor of 2 to 3 higher angular momentum than that in the Earth-Moon system today. So in order for this to be the way that our moon formed, requires that some later mechanism removed this angular momentum excess, essentially slowed down the spin of the Earth after the moon formed. A promising mechanism for doing this is the evection resonance with the sun. The moon's orbit is slightly eccentric, and it precesses primarily due to the oblateness of the Earth's figure. As the moon orbit tidally expands after its formation, it would have encountered the evection resonance when the lunar precession period matched Earth's orbital period about the sun of 1 year. Now, when the moon is in the evection resonance, the orientation of the moon's orbit maintains a relatively fixed position compared to the line connecting the Earth and the sun, with the periaps of the lunar orbit being about 90 degrees away from this line. And while in this configuration, evection can extract angular momentum from the Earth-Moon pair and transfer this angular momentum to the Earth's heliocentric orbit. I'm going to show you a simulation of the moon's evolution through evection and describe how this basic mechanism works. These simulations assume a constant tidal parameter for both the Earth and the moon, and we'll get back to that as being an important issue in a moment. The plot on the left is looking down on the Earth-Moon system. The sun is shown to the right in a frame that's co-rotating with the Earth. Orange shows the lunar orbit, and the dotted black line shows the position of the evection resonance. The plot on the upper right, the key line is the blue line that shows the total angular momentum in the Earth-Moon system and how it changes during time. Initially, the moon's orbit tidally expands until it encounters the evection resonance at a distance of about 8 Earth radii. Once it becomes captured in evection, the resonance increases the eccentricity of the moon's orbit and causes it to maintain this fixed orientation relative to the Earth-Sun line. Eventually, the eccentricity gets large enough that tides in the moon start to cause the orbit to contract. And at this point, the moon leaves evection proper and enters what we call a quasi-resonance phase, where that fixed alignment is no longer being maintained, but evection is continuing to keep the lunar eccentricity high. It's during this quasi-resonance phase that substantial angular momentum is extracted from the system, and it continues until the evection resonance passes within the moon's orbit. After that point, the moon's orbit continues in a typical tidal evolution scenario, expanding and conserving angular momentum. So the example I just showed is a successful one in that it starts with a system with a high angular momentum and has evection remove the appropriate amount of angular momentum from the system to leave us with an amount consistent with the current Earth-Moon. And we found by completing many of these simulations that the end result depends on both the strength of lunar compared to Earth tides, that's the A factor on the y-axis, but most importantly on the strength of tidal dissipation in the Earth, parameterized by Q, where a small q means fast orbital migration of the moon, and large q implies slow orbital migration of the moon due to Earth tides. We find that if the moon's orbit expands out too quickly, if the q of the Earth is too low, then too little angular momentum is removed due to evection. While in contrast, if q of the moon is, or q of the Earth rather, is too large and the moon's orbit expands too slowly, then the evection resonance removes too much angular momentum from the Earth-Moon system. And in between these two extremes is a range of successful parameters that remove the right amount for consistency with the current system. So we'd like to understand how probable those successful cases are. To do that, we need to do a better job at treating the strength of tidal dissipation in the Earth. These models assumed a fixed value throughout the evolution, but we know that Q of the Earth would have changed substantially as the moon encountered evection, as the Earth's mantle cooled. And so our current work is coupling this dynamical evection model to a physically realistic model for Earth mantle cooling and the associated dissipation in that cooling mantle developed by Jun Korinaga. Right after the giant impact, the mantle is molten. The Earth responds in a fluid-like way to tidal interaction with the moon, and the effective Q of the Earth is then very large. But as the mantle starts to solidify, dissipation in the mantle increases and Q begins to decrease. Finally, as the mantle is fully solidified, one will reach a point where the Q of the Earth is due to solid body and/or ocean tides.
3 minutes.
Thank you. You can see that the dashed line here is the position the moon encounters evection, and that the moon encounters evection as this process begins. This is my last slide, which shows you some initial results of this coupled model that look really promising. The top plot shows the evolution of the moon's eccentricity. The region indicated is where evection is keeping the eccentricity high, and on the lower plot, the angular momentum is being substantially reduced. This case didn't remove quite enough angular momentum for consistency with the current Earth-Moon, but it removed a lot, and so we consider this a very promising result. Our current work is we're completing a large suite of these simulations. They're very computation intensive, but again, the goal here is to determine how likely it is to have the angular momentum needed to make a high angular momentum giant impact viable. Thanks.
Is this Mike? Oh, I do. Thanks. So we're actually, Robin, we're a little bit early, so I can actually ask a question from the audience, but we'll have a discussion period later as well. Does anyone have a question?
Feel free to shout it out. The room is mic'd. Step one.
But I'll ask a question. So let's take advantage of this time. So the moon becomes very eccentric, and then eventually the eccentricity of the moon goes down over time. So that suggests that there must be a lot of heat being pumped into the moon at this time. Would you expect the moon to be fully molten or partially molten from the heating it gets during this period?
This is one of the important issues that we will be looking at carefully. It really depends on how the relative tides in the Earth versus the moon evolve. For example, in this particular case, the first one we've completed, the eccentricity of the moon stays quite low. It's less than 0.1 here. And so this is a low eccentricity evolution. But in contrast, the animation I showed you, the eccentricity of the moon gets much larger, and the dissipation in the moon would probably be substantial enough to keep it molten or to remelt it potentially. And so that's one of the key questions that will come from this wider suite of simulations that we're doing.